Hi everyone, here we are for the third day and final day of chapter 18, and we're going to finish up these elementary reaction kinetics concepts and then move on to the next chapter where we get to put all these pieces together and look at more complex reaction mechanisms. These are the three concepts we'll cover today. We'll cover the Arrhenius equation, then reversible reactions. So far we've only seen reactions that go in one direction, but reversible reactions can go backwards as well. And then we'll also take a look at potential energy surfaces, which closely relate to the Arrhenius equation and which can provide a really helpful way for thinking about kinetics and thermodynamics as well. So the Arrhenius equation was found empirically, so it's an empirical law that just seemed to match with experiment pretty well, and it tells us that we can predict the rate constant for some reaction, and this is going to equal a constant big A times e to the negative e sub little a, which is an activation energy, divided by RT, where R is the gas constant. This big A is called the pre-exponential factor. And this E sub little a, as I said before, is the activation energy. Okay, so what exactly is this equation saying? It says that there's a way to sort of abstract our concept of a chemical reaction. If down here I have the so-called reaction coordinate, then what that means is the reaction, the actual chemical reaction, is going to be somewhere along this axis, okay? And again, this is sort of an abstract concept, but over here, if the reaction coordinate is a small number, then that means that the reactants are being favored. But then if it's over here, then the products are being favored. And you've probably seen these types of plots before, but over here at the reactants side of the reaction coordinate, we've got a flat plateau and then a hill, and then the hill drops down to a different height. And this different height represents the products, and see how those are at different places. And this axis over here represents some sort of energy, okay? Now, the difference between the height of the reactants and the height of the products is some thermodynamic quantity. So that distance right there, it might be delta HR or it might be delta GR, just depending on what we're talking about. But this height right here, between the reactants and the top of this peak, this distance is that activation energy that appears in the Arrhenius expression. And there's also going to be another activation energy for that right there, and that is the activation energy that would apply to the reaction going in the reverse direction. So this activation energy would be for the rate constant of A going to B, and this activation energy would be the rate constant for B going to A, okay? And so depending on which direction we're talking about for the reaction, we would plug in a different activation energy. And you may have seen before with plots of this sort that a catalyst is able to lower this activation energy barrier and thus increase the kinetic rates of a particular reaction occurring. So this is what a catalyst does. And we'll see more about catalysts in the next chapter. But I'd like to move on a little bit and return to this expression up here for the Arrhenius equation. I'm going to now take that equation and take the natural log of both sides. So I get the natural log of K equals the natural log of A e to the negative activation energy RT. But I can use the rules of logland to just say that this is the log of A plus the log of e to the negative activation energy RT. And then, of course, the natural log cancels out with the e, so I get natural log of A minus activation energy times 1 over RT. Notice what I've got here. I now have a y equals mx plus b equation. There's my y, there's my b, and then this activation energy is my slope m, and then this 1 over RT is my x, okay? So if I plot the original Arrhenius equation, over here I might have this rate constant value, and then on this axis I would have the inverse temperature. The data points are going to make an exponential decay function, so an e function. And what Arrhenius originally did when he wrote down this equation is he didn't plot the rate constants against the inverse time. He plotted the log of the rate constants, and then down here he had negative 1 over RT, which is this expression right here, but with that little negative combined into it. And what he saw was that you get a linear function like so, and that intercept is the log of that pre-exponential factor, and the slope is the activation energy. And so this was the empirical relationship that he discovered, and the Arrhenius equation was the first of this sort that was written down. However, it's worth noting that there are some more advanced theories that use a modification of the Arrhenius equation. And an example of a different theory that doesn't use the Arrhenius equation, but a slight modification of it, is that the rate constant equals A times the temperature of the system raised to some power multiplied times e to the negative activation energy over RT. So again, we still have that exponential thing appearing, but see now the pre-exponential factor does depend on the temperature. And different theories will use different values for m. It might equal 1, it might be 1/2, it might be to the negative 1/2, and that just depends on the theory. By the way, there's an interesting note. They've done experiments where they found out that crickets, the frequency of crickets chirping seems to be described by the Arrhenius equation. If you take crickets and you put them in cold environments, they will slow down the rate of their chirping. But if you put them in hot environments, they'll speed up their rate of chirping. So whatever the mechanism is inside of crickets that is controlling their chirping, it seems to be controlled kinetically and can be described by the Arrhenius equation. Just sort of an interesting side note, interesting factoid there.